Okay guys, so I came across this some sort of emulator, but it's really fun. So this basically is for those people who are actually starting with studying neural networks. This will kind of show you how neural network works or digs into a problem and how it evolves. So we have like four types of data sets here. This is more of a classification problem. And then you have size of the data which you want, the batch size. It's more of a bootstrapping process, I guess, on which you're going to it's going to train. Then comes your learning rate, and your activation function. It can be ReLU, it can be 10H, sigmoid, linear. Keeping it so we can take this since this particular data set has got a lot of curves in it. I am taking 10 hyperbolic 10 function. Then comes your regularization if you want it or not. As of now I don't, because first of all I'll fit my model, then I'm going to introduce the regularization. And yes, this is a classification problem here. If I go into regression problem, the data set changes. See? So I'll start with the classification. I'll start with something like this. So in this there are two inputs, then two layers with 4 neurons in one and 2 in one. And then I run this. So in pretty much 168 counts or so, I am able this particular neural network is able to segregate. But we have to make sure that we get this done in minimum hidden layers and in minimum neurons. So if I reduce one hidden layer, let's see how it comes out. Cool. So as you can see, even with single hidden layer, it's working. Now I'll try to reduce neurons. So if you see, this will give you an idea of how it is doing. So you see this line, then comes this, then comes this, then comes this. Now this and this, these two neurons look similar, don't you think so? It has just got that slight slope difference. So I think if I simply, and you see, this is your weight. So weight of this is negligent if we compare that weight to others, 2.2, 1.8, 2.2, and this is your 0.55. So I simply remove one of the neurons and run this again. See, it was able to fit itself. And you see, another good thing about this is that the thicker the line means more the weight you have. So I basically did this full classification problem with single hidden layer and 3 neurons, and it's doing a very decent job over here. Now let's change the data set, and I did it with 10H. Let's say I use a ReLU function. So with 10H, if you remember, we were able to do in 200 or so. With ReLU, if you see, within 100, I would say less than 100 actually. Right. So with less than 100 iterations, it was able to do this, but there is a difference, you see. ReLU being a linear function, that's why it has got these lines around it, which is doing the job. And the 10H was more of since it has curves in it, so you see the boundary here will have curves in it. It's not a linear function. On the contrary, ReLU being a linear function, it's going to do this. So every time you run this, you might get a different shape, but the end task of classification will be done. Because it is running on the go, so it won't take the same learning path every time. It might take a different learning path. This also happens that, in one time it was able to segregate, but second time it ended up doing nothing. So that also happens with this. Now ReLU, let's go to a sigmoid function and see how it is performing. So with sigmoid function, as you can see, sigmoid function is expensive than your 10 function, but it is also a nonlinear function, so that's why giving these curves here. Coming on to a linear activation function. So linear activation function, you see, it's not doing anything. It's just running. Even if see, I increase the learning rate to 1 just to see where it will end. But as you can see, it is just, because linear function is nothing, just a line. So we know that single line cannot actually basically divide this region into 2, but that won't justify our problem because this will end up as being misclassified in this here. So linear function won't be of our help. 10H and ReLU will be. I just want to see if we can do this through ReLU with lesser neurons. Let's try this with 2 neurons. No, because this is again an interesting thing. Let's see if I further on decrease the learning rate so that it doesn't get stuck at a local minima, and see if ReLU comes along. See, I think this goes back to the fundamental. In order to close a space just with lines, we need minimum 3 lines. With just 2 lines, it's impossible to close a space. So that is the reason you have 2 neurons, whatever you want to do, it's not going to close this space. But with 3 neurons, it will be done in no time. You see, it is already starting since the learning rate is less, so that it doesn't end up at the local minimas. And here you go. See, the classification is done. Light yellow means the lesser probability, dark yellow means higher probability. So that's how it is. And these things. Now let's move on to another data set. For example, this one. Now these are some of the activation functions which we can apply on the input layer itself. Now looking at this, we know that this can be straight away done with a linear activation function. So if I simply go here to the linear activation function with single neuron, and see, it did. So they basically just with single perceptron, I would say it worked for us. Coming here, we need 2 lines, remember? So if I do a linear activation function, but if I do a single neuron, it won't be of any help. Let me increase the learning rate so that it's a bit quicker, because linear activation functions are quicker. It's not doing anything. Let me make it 2. With 2 linear activation functions with a faster learning rate, you see, still it's not of much help. But how about if I use this? If I create another feature by multiplying the 2 and see how it comes out. See, it did. And I think we can see with single neuron. And this is nothing. What I did was just the optimization of the full neural net. So with a single neuron, it did the job. With a linear activation function, I just want to see in how many. So with under 30, if I do a proper feature engineering and then I pass it to a neuron, with under 30 epochs, it was able to do with linear. But if I do with ReLU, let's see. Whoa. Since this data set is too simple, that's why it's going pretty fast. Let me change the data set. Now this is a trickier one. It's an spiral data set where we have x1 and x2. Now, if you see this spiral data set with single neuron, doesn't matter. Let me take it to the highest and let me take the learning rate as this and see how this turns out to be. You're seeing this test loss. This is nothing but the amount of data which is getting misclassified. So this we have to decrease. Training loss, test loss. So with the ReLU, as you can see, it is converging very slowly, but still it's taking some time and stuck. If you see, it's just stuck over here. Let me change the learning rate to 0.003 and we started. Let's see. You see these values, they are going down, and the place where it stucks is the place where the function is hitting a local minima. That means it has more scope to go down, but because of high learning rate. See, if I do this, if I put a learning rate as high as 3, see, this is your loss. Basically everything is going off. Now I put a decent learning rate, I put a decent function, I add one more layer, 8 neurons. Let's say we put another layer with 3 neurons, 4 first, and see how it converges. So our expectation is some sort of a spiral should be built with blue spiral like, and it is actually, see, you see this blue spiral is coming up, and this yellow spiral is basically your yellow. Here these 2 points are under the misclassification zone, and it is slowly going under the right one. Similarly, these points should also come under the yellow zone, and this is your overfitting, you see. And now see, the score is suddenly fluctuating. That means that it has hit a local minima, or I would say it has actually got the job done. It is basically overfitting. So we'll pause it there itself, and now we'll analyze these neurons. Oh, to my knowledge, if I compare this and this, you see, second, we'll see the weight. So pretty much if the weight is, so weight is a measurement which shows that pretty much all the neurons are dominating. But you see here, the weight here actually, you can, I think I can decrease a couple and see if this can be done with lesser neurons, because for this we for sure will need 2 layers, but let's see if it converges with lesser number of neurons per layer. And yep, it's getting a shape, and suddenly it's balancing the, you see the training loss, this has to go down, so it is basically going to catch that shape. So it is also pretty much doing a good job, but it is again overfitting. You see, even the gap it is trying to fill with blue. So that means even with lesser neurons, it should do the job. So that's how you play around with this stuff, you analyze, but it gives you an idea of how the combination of neurons, the combination of learning rate and activation function, plus the initial ones which you can do, affect the things. So these are squares. So if you want the square values to go in, again some sort of feature engineering which goes in here, and then so see here some spiral shape is again forming up. Training loss is decreasing, but it is slow. Point, it is going on, it's decreasing, which is fine, but it is again overfitting. So we want to bring it down. So yep, I leave it to you guys to analyze and see. And yes, this is how you can basically see or visualize how the working of uh, neural net, perceptron, and layers, and your activation function. How do they differ, and 10 different things. So that should be it, guys. Bye bye. Take care.